Hi everyone, we're going to begin by looking at oscillatory motion. Oscillatory motion is repetitive motion back and forth about an equilibrium position. It's periodic, meaning that it repeats in equal intervals of time. An example of this is a pendulum, or a mass on a spring, or vibrating objects such as a guitar string or atoms in a solid. We'll first look at the most basic type of periodic motion, which is simple harmonic motion. Simple harmonic motion is periodic motion that occurs with no losses in energy. So let's consider a simple mass on a spring system. Looks something like this. This is a horizontal mass on a spring. If it was displaced, it would oscillate back and forth between x equals negative a and x equals a. So this occurs because it has a restoring force that always pulls it back towards equilibrium. This is a stable equilibrium, meaning that if it was displaced slightly, it would always come back to equilibrium. And that's why this motion occurs and is periodic. It would also occur indefinitely unless it is stopped by some kind of external force, since there are no losses in energy. Okay, let's look at some basic definitions that describe oscillatory motion. I'm going to go through these definitions in reference to the mass on the spring system, but they do apply to all periodic motion. So the first definition is amplitude, and this is where the A comes from for a maximum displacement, because the amplitude is the maximum displacement of the mass from its equilibrium position. So if this mass is initially displaced a certain amount, that becomes the amplitude of the motion, and then it will oscillate between A and negative A. This is a length or a displacement which is measured in meters. Then we have period, which is capital T. Period is the time required for the mass to complete one cycle of its motion. Now, it's important to know that one cycle here means there and back. So the mass has to return to the same position where it initially was, but also be moving in the same original direction to have completed one cycle. So that's fairly clear if it's starting here at x equals a. However, if it started at the equilibrium position, it would have to travel there and then all the way back so that it's again traveling in that same direction as it was originally. And that's one full cycle. It's a time, so it's measured in seconds. Okay, then we have frequency. The frequency is the number of cycles that occur per unit time. So the symbol for frequency is lowercase f, and it's measured in units of hertz, where 1 hertz is 1 seconds inverse. That's what the hertz unit means. The relationship between frequency and period is that period is 1 over the frequency. There's another quantity that's often used for oscillatory motion, and that's angular frequency. The symbol for angular frequency is omega, and it's measured in radians per second. Though radians is a unitless quantity, often in physics we will write that just to show how the unit analysis works out. So omega is related to the frequency by omega, angular frequency, equals 2 pi f. We could also say 2 pi over the period since they're inversely related. Now, the angular frequency means the rate of change of the phase per unit time for oscillatory motion. An easier way for now to think about this is angular speed, which would mean the rate of change of the angular displacement per unit time. And we'll look a little bit further into what this means as we compare to circular motion. Okay, let's consider this mass spring system. So if the mass is initially displaced at x equals a, it has a speed of 0 at that point. Anytime it reaches x equals a or negative a, its speed is 0. These points are called the turning points. Then as it passes through equilibrium, that's where it will have its maximum speed at x equals 0. Let's plot out its displacement on a graph. So if it's starting at x equals a, then after half a period, it's at x equals negative a, and after a full period, it returns to its starting point at x equals a. If we continue with this, we actually have a sinusoidal function. So this means either a sine or a cosine function. Often for simple harmonic motion, the displacement is written in terms of a cosine function. So the expression is x at t equals a cos omega t plus phi. A is the amplitude in meters. Then we have omega, the angular frequency in radians per second, times time, plus phi. Phi is a constant called the phase constant that determines the initial position. So, for example, here where I've chosen for the mass to start at x equals a, phi would be equal to 0 to give us x at 0 equals a. So that constant will change based on where the mass starts. Also based on its initial speed, but we'll get into that a little bit later. Now we could have written this in terms of a sine function, it would just have a different phase constant. So you can always write this in terms of either sine or cosine, just make sure that you have the correct phase constant. So we know that sine theta equals cos of pi over 2 minus theta. That's why we could shift this and write it in terms of sine or cosine. Okay, so let's look further into this equation for displacement. If we look at this horizontal spring, then the forces in the y direction are balanced, and in the x direction we just have the spring force. You should remember from your previous physics class that the spring force Fs equals negative kx, and this is Hooke's law. So we have k, which is the spring constant, gives a measure of the force per unit length for the spring, and is measured in newtons per meter. And then x is the displacement. The negative sign here indicates that the force is opposite to the displacement. And then I hat shows that it's in the x direction. So if we write the net force in that direction, we have the net force in the x direction equals Fs, which is negative kx, and that has to equal ma since it's the net force. So we have, rearranging this, the acceleration is the second derivative of the position or the displacement. So we have d squared x by dt squared equals negative k over m x. And this is the characteristic differential equation for simple harmonic motion. And if the solution of this is x at t equals a cos omega t plus phi, if we have omega squared equal to k over m. So we now have another equation for the definition of the angular frequency. It's equal to the square root of k over m. So any object in simple harmonic motion will be subject to the following differential equation and will experience a restoring force that is proportional to its displacement. Let's note that this displacement function, x at t equals a cos omega t plus phi, it behaves the same as any cosine function. So if you recall, cos theta is bounded by negative 1 and 1, and x at t equals a cos omega t plus phi is bounded by negative a and a. And then cos theta will repeat the cycle whenever theta increases by 2 pi. This function will repeat whenever what's in the argument, omega t plus phi, increases by 2 pi. So then I just wanted to also note that with this new relationship for omega, which is root k over m, we know that the period is 2 pi over omega. Before I said omega was 2 pi f. So plugging in the period, we get periods 2 pi over omega, and then we plug in omega, and we have this nice relationship to find the period of the mass on the spring. So the period's 2 pi root m over k. So that means it's just dependent on the mass and on the spring constant. Okay, so far we've seen a few characteristics to define simple harmonic motion. Let's just summarize them. The first was that it's periodic motion that occurs with no loss in energy. Second, there is a restoring force that's proportional to the displacement. Its position and velocity, we'll see, and velocity functions are sinusoidal. And it's subject to the following differential equation. This one, I wrote it again here. D squared x by dt squared equals negative omega squared x. Okay, let's just compare to circular motion and then we'll do some examples. Okay, angular frequency is the same variable as angular speed here because the displacement of an object in simple harmonic motion follows the same relationship as the x component of the displacement of an object moving in uniform circular motion. So the x component would be here for the displacement, And that would follow the relationship of x equals r cos theta. I can draw theta in. And then if we say theta equals omega t plus phi and r equals a, the amplitude of the motion, we have the exact same relationship here for that x component of circular motion. So you can think about it like that as the angular displacement per unit time. It makes more sense physically to picture that for a pendulum, but it still applies for any object in simple harmonic motion since it still follows this relationship. Or you can think of it as the rate of change of the phase, which is this quantity, per unit time as well. Okay, so example 1 says show that x at t equals a cos omega t plus phi satisfies d squared x by dt squared equals negative omega squared x, which is the differential equation characteristic to simple harmonic motion. So let's start by taking the first derivative of this displacement function. We have dx by dt equals, the derivative of cos is negative sign, so I'm going to put negative. This omega will multiply in front when I take the derivative of the inside. So we'll have negative a sine omega t plus phi. Okay, and now I'll take the second derivative. So d squared x by dt squared equals, derivative of sine is cosine, so the negative sign will remain, and then we'll get another factor of omega from taking the derivative of the inside again. So negative omega squared a cos omega t plus phi. And we can see that this, a cos omega t plus phi, that is our x at t function. So we end up with d squared x by dt squared equals negative omega squared x. And that's what's expected, so we're showing that the solution does satisfy that differential equation. Example 2, a vertical spring stretches by 3.9 centimeters when a 10-gram object is hung from it. The same spring and mass are placed on a horizontal frictionless surface and set into simple harmonic motion. What is the angular frequency and period of the motion? Okay, so let's sketch this out. I've done it already. It looks like this. And the spring has been extended when this mass is placed on it. We can use that and Newton's first law in order to determine the spring constant of the spring. So drawing the free body diagram looks like this, Fs, which is up, and Fg, which is down. And then we have the sum of all the y forces equals 0 since it's initially at rest. So Fs must equal Fg. So we have Kx equals mg. I've already accounted for the direction that it's up, so I'm not including any negative sign here. The negative sign in Hooke's law, if we write Fs equals negative kx, that just means that the direction of the force is opposite to the displacement, and it's displaced down, so the force would be up here. Okay, and then we can solve for k, so k equals mg over x, which is 10 grams, so 0.010 kilograms times 9.8 newtons per kilogram over 0.039 meters, so 2.51 newtons per meter. And now it's rotated, now it's on a horizontal surface, and we can look at the frequency and the period of its motion. We know the angular frequency will be the root of k over m, so we can plug that in, the root of 2.51 newtons per meter over 0.010 kilograms, so 15.8 radians per second. And then the period is 2 pi over omega, so 2 pi over 15.8 radians per second. This is technically radians here too, if you want to write it just to see where that cancels. It's not completely necessary, but we get 0.398 seconds for the period of the motion. Example 3, a 7 kilogram object is hung from the bottom end of a vertical spring fastened to an overhead beam. The object is set into vertical oscillations with a period of 2.60 seconds. Find the force constant of the spring. Okay, so the theory we've looked at so far for horizontal oscillations also applies to vertical oscillations. The only difference is that the rest length of the spring would change. It would now be lower since there is initially a mass attached. But okay, so we have a period given, so we can use that in order to find k, which is the unknown. I'll write that here. K equals. So we know t equals 2 pi over omega, and omega is root k over m, so we have the period is the root of m over k. And then we really just want to use that period to solve for k. So squaring both sides, I have t squared equals 4 pi squared m over k. And solving for k, I get k equals 4 pi squared m over t squared. So that's going to be 4 pi squared times 7 kilograms over 2.60 seconds squared, which is 40.9 newtons per meter. Okay, let's now talk about the velocity and acceleration of an object in simple harmonic motion. So we've been working with this function for displacement, x at t equals a cos omega t plus phi. To find the velocity of the object at time t, we can take the first derivative of this function. So vx equals dx by dt. The derivative of cosine is negative sine, so I have negative, and then I'm multiplying out the derivative of the argument here using the chain rule. So that omega comes out in front, and the derivative of the phi is 0. So we get negative omega a sine omega t plus phi. Now sine can also vary between negative 1 and 1, so at the maximum its magnitude is 1. So the maximum speed is equal to omega a. And then we can do something similar to find the acceleration. So we have ax equals dvx by dt equals, now the derivative of sine is cosine, taking the second derivative of displacement or the first of velocity, and multiplying out another factor of omega for the derivative of the inside. So I have negative omega squared a cos omega t plus phi. Again, cosine varying between negative 1 and 1 shows us that the maximum acceleration for the object is equal to omega squared a. And we don't have those formulas necessarily, but we can see that really easily by comparing to these velocity and acceleration functions. And we'll look at plotting these as well. I want to talk a bit more about the phase constant phi. So if we look at this mass on a spring that's starting at x equals a, its displacement graph would look like this. You can actually just map out how the mass would move and plot each point and then fill in the shape. So we know it would start at x equals a, and then one period is when it goes all the way there and all the way back. So after one period it's back at x equals a. After half a period it's at this other endpoint at negative a, and then at each quarter period it's passing through equilibrium. So we know this is modeled by x at t equals a cos omega t plus phi. And this phi will just shift the trig function to give a different starting point depending on what we put for phi. So if phi equals 0, that's when we have x naught, x initial, equal to a. If we had phi equals pi over 2, then we would have x initial equals 0 if we plug that in here. And then if we had phi equals pi, this one would give us x equals negative a here. Just plugging that in again. So we can choose, it doesn't have to be a nice starting point either, it could be anywhere in between, and phi will give us that initial position. And we could also use sine here, which would then give us a different range of phase constants phi. Alright, example 4. An object oscillates with simple harmonic motion along the x-axis. Its position varies with time according to the following equation. X equals 4 meters cos pi radians per second t plus pi over 2 radians. A, determine the amplitude, frequency, and period of the motion. B, determine the velocity and acceleration functions, and C, plot x, vx, and ax. Okay, so just by comparing to our standard simple harmonic motion equation, we have a cos omega t plus phi. This tells us A is 4 meters. Then we have omega is pi radians per second, and that angular frequency will allow us to find the period and the frequency of the motion. So we'll have, there's a few ways to go about it. Let's find the period first. It's 2 pi over omega, so we get, that equals 2 pi over pi, so 2 seconds. And then the frequency is 1 over the period, so 1 over 2 seconds, which is 0.5. Or leaving it as a half is equal. So you could have done those in the opposite order, right? Found the frequency first and then gone to find the period. Okay, now for B, we want to find the velocity and the acceleration functions. Let's do the specific derivative by looking at this equation here. So the velocity will be dx by dt. So negative sign for cosine, and then I'm going to multiply the pi, so negative pi radians per second times 4 meters sine, and inside we have pi radians per second t plus pi over 2. Again, not super important if you want to write radians or not, since it is unitless. I'll usually write it. Okay, so that's our velocity function. This is negative 4 pi essentially, and then for acceleration we have dvx by dt. So taking the derivative again here, the negative stays and we get pi squared when another factor of pi multiplies out times 4 meters. Then I'll have cos pi radians per second t plus pi over 2. And we could simplify this a little bit, but it's also okay to leave it like that. And then I'll move this up. We want to now plot all three functions. So we're going to plot x at t, vx, and ax. So let's check our x function, x naught, which is x at 0, t equals 0, equals 4 meters, cos pi, this is pi times 0, so we have 0, plus pi over 2 radians. So just putting that back up for a second. Okay. So this is cos of pi over 2. And so if we do that, we get 0, since cos of pi over 2 is 0. So this is actually starting at 0. Now this means that it's actually shifted by 1/4 from the phi equals 0 function, a quarter period. However, let's also check our sign of the velocity at 0. So if I was going to plug in to find v naught here, v naught would be sine of 0, and then this is pi over 2. So sine pi over 2, which is 1. So we get v naught would be negative 4 pi meters per second. And so we know that it's going to be moving in the negative direction initially, so that will help us plot our graphs as well. So okay, let's start with the position function here. X, let's do 2 periods, so that's 2 seconds. Here's 1 second, and then we'll have the quarter periods in there. Oh, sorry, I'm just doing 1 period at 2 seconds. Okay, so we know it's starting at 0, and we have our x equals a, which is 4 meters and negative 4. And then it's going to go in the negative direction, so down first to here, and then back through equilibrium, and up to positive a, and then ending back at 0 here. And then you can fill that in so that we have our sinusoidal shape. Okay, so now let's plot our displacement. Got some room down there to plot velocity. So here, t Vx, and then this will go from 4 pi, say that's in meters per second, to negative 4 pi, so 0. And again, let's do the same time period, just one period. Now, our velocity function will always be shifted by a quarter cycle from the displacement. From x at t. That's always true for any of these functions here. So we can just think about shifting it. If this is a full period, this is a quarter. So I'm going to start my graph there, cover that up, and then we have our function continuing. But we could also map out based on our initial condition. We know it starts at negative 4, and then it's going to be slowing down as it reaches the end point there. So here, here, moving up to the maximum, and then back through equilibrium to there, and then filling in the sinusoidal shape. Okay, and we have one left to do, which is going to be the acceleration. So I'll just move this a bit so I have some room for that. There we go. Okay, so right here, AX, and then we have 2 seconds, 1, and the period. Now our acceleration graph is always shifted ahead 1/2 cycle ahead from x. So, okay, move that up even more. So that's what I was meaning originally, was that our velocity function is shifted a quarter ahead from displacement, and acceleration is shifted a 1/2 cycle ahead. So if I'm going to block this at a 1/2 cycle, then we know that it will continue this way for acceleration. But again, we can also just plot it based on the derivative function that we found in part B. So when I do that, we have starting at 0, the acceleration at the equilibrium position, and then it's going to go up at the quarter period, back through 0, down and back to 0 at the very end for one full cycle. So filling that in like that. So okay, there we have all three just fitting into my plot here, and then you can compare either by shifting or just by looking at the individual function and marking out each point, whichever is easiest for you there. So again, that's the acceleration, just to make that a bit more clear. Okay, in the previous example, we were given a and phi, and then we used those to graph the functions. Let's say instead we're given x naught and vx naught. We can still find the amplitude that way, just by doing a bit of algebra. So the initial conditions, x naught will be a cos phi, setting t to 0. And v naught will be negative omega a sine phi. So we want to combine these two functions in order to find the amplitude. And the trick to do that is to square x naught plus vx naught over omega, square that, and add the functions. So we'll have a squared cos squared phi plus omega squared a squared sine squared phi. And then this I've divided by omega, so I have that over omega squared. So that factor will cancel. And then we get a squared cos squared phi plus sine squared phi. And this is an identity. Sine squared phi plus cos squared phi, or theta, equals 1. So then we end up with a equals the root of x naught squared plus vx naught squared over omega squared. And that will allow us to find the amplitude if we're just given those initial conditions. Then we can also find the phase constant. So how we're going to find the phase constant is that we can solve for it by using the initial condition. So we can do cos phi equals x naught over a, and then this will give us phi. So phi is cos inverse of x naught over a. Now, I want to remind you that this will give you two solutions. So sine and cosine and also tangent are trig functions. For most angles, for most values, they're going to have two angles or two arguments that will give you that same cosine value. So cosine, if you remember this, the cast rule, so we have cosine is positive in this lower quadrant 4 and quadrant 1. So if you do this, it may just give you the solution here, but the solution below that is also an option. So remember to check both, and how we're going to know which one is the right solution is we're going to check the sign of the velocity. So check the sign of Vx naught. So we do have Vx naught equals negative omega a sine phi, so you can just plug both of these in here and see which one will give you the right sign, and that's the one that you choose to use for your phase constant. Let's do an example. A spring with spring constant K equals 200 newtons per meter is suspended vertically and a 2 kilogram mass is attached to the other end. The mass is pulled down 10 centimeters from equilibrium and released. As the mass passes through y equals 0, moving up, the clock is started. A, what is the angular frequency and period of the motion? B, what is the equation of motion for the displacement of the mass? C, find the velocity and the acceleration of the mass at 1.5 seconds. Okay, so for A, we're looking for the angular frequency and the period. Those are just formulas we can plug in here. Omega is root K over M. So the root of 200 newtons per meter over 2 kilograms. So that's 10 radians per second for the angular frequency. Okay, and then the period is 2 pi over omega. So 2 pi over 10, which you can leave as pi over 5 if you'd like, and that's seconds, or 0.628 seconds. Okay, so now for B, we want to write out the equation of the motion for the mass. So we know, put B here, let's use some space up here. We know it's going to look like this, A equals cos omega t plus phi. So the question is asking us to fill in these parameters for A, omega, and phi. Okay, so we have omega, we have A, which is 10 centimeters. And then the initial conditions are that when it's moving up, the clock is started here. So Vx naught is positive and x naught is 0. So let's use x naught. We have x naught equals, this t is 0, so A cos phi. So we'll have phi equals cos inverse x naught over A. So basically cos inverse of 0 which gives us phi equals plus or minus pi over 2. So two things, you can do this in your calculator and you'll get pi over 2, but make sure to check this cast rule since we know there are two solutions. We know this one is both here, plus or minus pi over 2. Also, just a reminder to use radians for this section. So if you did have other numbers, this one we don't really need our calculator, but other numbers, make sure that you're in radians. Okay, and so now we don't know which one to choose, so we'll go to the velocity and check the sign there. So the initial velocity is going to be negative omega a sine phi. And I don't need the actual value, I just need the sign because I know that we want it to be positive. So if I plug in V naught is negative omega a sine pi over 2, pi over 2 is positive, this is negative, which would give me a negative velocity. And we know that that's not correct, we want positive, so we need V naught equals negative omega a sine negative pi over 2, which gives us a negative 1 times omega a. So that's going to be omega a positive, which is what we wanted. So we know we're going to go with this solution of negative pi over 2. So that's what I mean by check the angle. And it's not always a nice number like this, so make sure that you do just adjust to find the second angle before writing it in the equation of motion. So we'll have x equals our amplitude 10 centimeters, so 0.1 meters, cos 10 radians per second, t minus pi over 2. Okay, now we can do part C, not part D. So I'm going to find the velocity using this function here. So Vx, we'll do that at 1.5 seconds. I'll plug it in since we just need that time. But this will be multiplying omega in front, and the derivative of cos is negative sign. So negative 0.1 meters times 10 radians per second, sine 10 radians per second, times 1.5 seconds minus pi over 2. So make sure to have radian mode, and then you can plug that into the calculator, and that will give negative 0.76 meters per second. And then AX at 1.5 seconds, we've done the derivative a few times, so what we'll have is negative omega squared, 10 radians per second squared, A. This is cosine, 10 radians per second, 1.5 seconds minus pi over 2. And then plugging that one in will give negative 6.5 meters per second squared.